Section 10.4 is absolute and conditional convergence. So far we've taken a look at positive series, but we don't really have that ability or that tool set yet to take a look at some kind of a series with both positive and negative terms. So we need to take a look at understanding this idea of absolute convergence. The definition, absolute convergence, is that the series summation of a sub n converges absolutely if the summation of the absolute value of a sub n converges. So we can verify this with this example using the absolute value of it. If you take a look at it, we have negative 1 to the n minus 1 power over n squared. So it's essentially just alternating signs in the numerator, and the denominator is growing based on the base. So we're going to show that this converges absolutely by showing that a summation as n equals 1 to infinity, absolute value, negative 1 n minus 1 over n squared, which would be equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, dot, dot, dot. So this is a convergent p-series, right? Because p, which is 2, is greater than 1. So therefore, we would say this converges absolutely. Now, technically, we only proved that the absolute value converges absolutely. So this theorem, though, oops, I'm sorry, it's on the next page. This theorem right here then allows us to make a more general statement about the original series. So the theorem 1 says absolute convergence implies convergence. So if the summation of the absolute value of a sub n converges, then the summation of a sub n also converges. So this example is literally the same exact thing, and we can make the statement that by theorem 1, this converges because we just proved absolute convergence in example 1. Okay. So example 3 is saying, does S, which equals the summation from 1 to infinity of negative 1 to the n minus 1 power over square root of n, converge absolutely? Okay. So the first thing we can do, right, is acknowledge that negative 1, n minus 1 is just alternating back and forth. So we really could look at this series, n equals 1 to infinity of 1 over square root of n, and acknowledge that this is a p-series with p equaling 1/2. Therefore, it diverges. Right? Any p-value other than p's that are greater than 1 diverge because p is less than 1, right? So therefore, S, the original series, also does not converge. Okay. A definition and another theorem here. So conditional convergence is that an infinite series converges conditionally if the summation of a sub n converges, but the summation of absolute value of a sub n diverges. You might be saying, well, how is this possible? So let's take a look at a few examples. And then we have this Leibniz test for alternating series. So if we're assuming that the sequence a sub n is a positive sequence that is decreasing and converges to 0, or in other words, the limit as n approaches infinity is 0, then the following alternating series would also converge. So if we just take that negative 1 to the n minus 1 power and put it in front of the a sub n, the decreasing convergent to 0 sequence or series, then we would have that the series also converges. And furthermore, we would be able to show that the sum is greater than 0 but less than a sub 1, right? Because the a's decrease in value and they approach 0, and that the sum is greater than this s sub 2n, but less than s sub 2n plus 1 for n being greater than or equal to 1. So we'll look at example 4 here. So we're going to show that the summation from 1 to infinity of the negative 1 to the n minus 1 over square root of n converges conditionally, and show that s is between 0 and 1. Okay, so again, we want to first show that a sub n, which is 1 over root n, right, it is a positive when n's are greater than 1, but it's decreasing. And we can show that the limit as n approaches infinity of a sub n equals 0, right? So because of this, we can then say S converges by Leibniz test. And we can further say that this sum is greater than 0, right? But it's going to be less than or equal to 1 because a sub 1 is 1. And therefore, if we have this alternating sign sequence and we find the series of it, sum it up, right, all of those values will essentially cancel each other out, and the largest one, which began as 1, must be larger than the overall sum. And then furthermore, because we've shown in a previous example, we talked about this, that the series 1 over root n diverges because it's a p-series with p less than 1. Therefore, this series S is conditionally convergent. Not absolutely. Right. Okay, theorem 3 in this section. Let S equal the series from 1 to infinity, alternating negative 1 n to the n minus 1 power times a sub n, where a sub n is a positive decreasing sequence that converges to 0. Then the absolute value of S minus S sub n, right, so the positive value there, is going to be less than a sub n plus 1. Or in other words, the error committed when we approximate S by using some finite S sub n is less than the size of the first omitted term, the very next term, a sub n plus 1. So we're going to show that this series converges conditionally, and then we're going to show that this error, right, is less than 1/7 for S sub 6, and we want to be able to find an n such that S sub n approximates S with an error less than 10 to the negative third power. Okay? So first of all, showing converges conditionally. A sub n is 1 over n, which is positive and decreasing. And if we took the limit as n approaches infinity of a sub n, we would get 0. So by Leibniz, S converges. Okay. But the series 1 over n does diverge, so therefore S converges conditionally. Right, if we didn't have it as an alternating, then this wouldn't be true. All right, so then the next part A, where n equals 6. Right, so we're saying that S, absolute value of S minus S sub n, is going to be less than a sub n plus 1, which is equivalent to 1 over n plus 1. So we're really saying S minus S sub 6, absolute value, is going to be less than a sub 7, and a sub 7 is a seventh. Okay, so that's all the work that would be required right there. And then part B, actually, let me start part B up here. We need a little bit more, and some of the evidence is proven in another section later on in the chapter, but I'll recall what they are giving us, and we'll take a look at it later on. Okay, so part B, in order to show that this error is less than 10 to the negative third power, first of all, we want to make this statement that 1 over n plus 1 is going to be less than or equal to 10 to the negative third, and we want to manipulate this, right? So this is equivalent to saying that n plus 1 is greater than or equal to 10 cubed, and therefore n is greater than or equal to 999. Okay, so we're going to specifically look at s sub 999, which is equal to, approximately equal to, I should say, using a computer algebra system. So this is coming from the textbook, 0.69365. Right? And then it does say in the book that later on in 10.7, it's proven that S, later on proven that S is equal to ln of 2. Okay. And ln of 2 is approximately equal to 0.69314. So therefore, box this off, the absolute value of S minus S sub 999, which is approximately the same as absolute value of ln 2 minus 0.69365. And this is approximately equal to, if I do those two subtractions, 0.0005, which is less than 10 to the negative third power. Okay. So that is the last example for this section. And then just in summary, bringing everything together, the idea of converging absolutely versus the conditional convergence, Leibniz test, and just summarizing the two ways to handle non-positive series.